triangles, circles, squares, simple shapes that even a child can draw. But what if these simple shapes describe every law of the universe we live in? Today, let's embark on a journey through geometry, starting from ancient Greece 2,500 years ago through 18th century French probability theory to what's called the most beautiful equation in mathematics. We'll uncover the secrets of how simple shapes describe reality. First, the Pythagorean Theorem. Why has this simple equation about triangle sides survived for 2,500 years? Next, pi. Why does this irrational number that goes on forever create a perfect circle? Then Buffon's needle. Why can we calculate pi just by dropping needles on the floor? Finally, Euler's formula. Why do the 5 fundamental constants of mathematics fit into a single equation? Now let's head to our first destination. Let's begin with the simple and beautiful theorem discovered by Pythagoras in ancient Greece 2,500 years ago. In the 6th century BCE ancient Greece, the philosopher Pythagoras was exploring the harmony between mathematics, music, and the cosmos. The theorem he discovered is remarkably simple. In a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. A squared plus b squared equals c squared. This simple equation has supported the foundation of mathematics for 2,500 years. But why does this equation work? We'll prove this theorem using 3 different methods. First, the most visual and beautiful proof, the square rearrangement proof. Consider a square with side length a plus b. Let's arrange 4 identical right triangles inside the square. In the first arrangement, a square with side c appears in the center. The area of the large square equals the sum of the 4 triangles in the central square. Now let's arrange the same 4 triangles differently. This time, a square with side A and a square with side B appear. The area of the large square hasn't changed. Therefore, c squared equals a squared plus b squared. By simply moving shapes, we've proven an algebraic equation. The second proof uses similar triangles. This is a more algebraic approach. From the right angle of the right triangle, drop a perpendicular to the hypotenuse. This divides the original triangle into 2 smaller triangles. Remarkably, these 2 smaller triangles are similar to the original triangle. All 3 triangles have the same shape. In similar triangles, corresponding sides have equal ratios. Using this property, we can derive a squared plus b squared equals c squared. The third is the most intuitive proof, the water proof. Place square containers on each side and fill the squares on sides A and B with water. Pour all this water into the square on side C, and it fits perfectly. The water proves that the areas are equal. We've arrived at the same truth through 3 completely different methods. This is the beauty of mathematics: geometric manipulation, algebraic ratio calculations, and physical water experiments. Every approach reveals the same universal truth. A squared plus b squared equals c squared. Hidden within the simplicity of this equation is the deep harmony of the universe. The Pythagorean theorem was a law of straight lines and angles. But what about the world of curves? Next, let's journey into the mystery of circles, the world of pi. The circle, the most perfect shape in nature, its beauty has captivated mathematicians throughout history. The ratio of a circle's circumference to its diameter. This simple ratio produces an endlessly mysterious number, pi, approximately 3.14159. In ancient Greece around 250 BCE, the mathematician Archimedes devised a brilliant method to calculate pi. He inscribed regular polygons inside a circle and circumscribed them outside. As the number of sides increases, the polygon approaches the circle. From a hexagon with 6 sides to 12 sides to 24 sides to 48 sides to 96 sides. With each step, the approximation of pi becomes more precise. Through this method, Archimedes proved that pi lies between 3.0408 and 3.0229, a remarkable achievement over 2,000 years ago. Pi is an irrational number. It cannot be expressed as a simple fraction. Its decimal expansion never ends and never repeats. Even more remarkably, pi is a transcendental number. It's not the solution to any polynomial equation with rational coefficients. 3, 1, 4, and 1, 9, 2, 6, 5, 3, 5, 8, 9, 7, 9. The digits continue forever without pattern, yet this infinite chaos creates perfect circles. Pi appears everywhere in nature. The period of a pendulum, the ripples on water, the spiral of galaxies. Even rivers. The ratio of a river's winding length to its straight-line distance averages to pi. And pi appears in the most unexpected places in mathematics. We'll see this in Euler's formula later. A number that goes on forever without repeating, yet it defines the most perfect shape. This is the profound mystery of pi. Simple enough for a child to understand, yet complex enough that mathematicians still study it today. Pi connects the finite to the infinite. But there's an even stranger way to find pi. Not through circles at all, but through random chance. Next, we'll discover how dropping needles can reveal pi. France, 1777. Count Georges-Louis Leclerc de Buffon proposed a remarkable experiment. An experiment that would reveal pi through pure chance. Draw parallel lines on the floor, each separated by a distance d, then drop a needle of length L onto this surface. Here's the surprising question. What is the probability that the needle crosses one of the lines? And what does this have to do with pi? Let's drop 10 needles. Some cross the lines, some don't. We count the crossings. Now 100 needles, the ratio of crossings begins to stabilize. With 1,000 needles, something remarkable emerges. The ratio converges to a value related to pi. Why does pi appear? Let's derive the mathematics behind this phenomenon. The needle's position is determined by two variables: x, the distance from its center to the nearest line, and theta, the angle it makes with the lines. The needle crosses a line when the vertical projection of half its length exceeds the distance x. That is, when x is less than L over 2 times sin theta. The probability equals the area satisfying this condition divided by the total area of possible positions. Integrating, we get the probability P equals 2L divided by Pi times D. Rearranging for Pi, pi equals 2L divided by P times D. By measuring the crossing probability, we can calculate pi. This is the beautiful intersection of probability and geometry. Random events revealing geometric constants. Buffon's needle was a pioneer of what we now call Monte Carlo methods, using randomness to solve deterministic problems. From ancient geometry to probability theory, we've seen pi appear in unexpected places. Now let's journey to the crown jewel of mathematics, Euler's formula. In mathematics, there exist 5 fundamental constants. Each emerge from different areas of mathematics, yet destiny would unite them. 0, the number that represents nothing, yet makes everything possible. The foundation of our number system. 1, the unit, the building block of counting, the multiplicative identity. Pi, the circle constant we've explored, the ratio that defines all circles. E, the natural base, approximately 2.71828. It governs growth, decay, and continuous change. And I, the imaginary unit, the square root of -1. It extends numbers into a new dimension. Can these 5 constants from such different origins possibly fit into a single equation? The answer is yes. Leonhard Euler discovered a profound connection. E to the power of I theta equals cosine theta plus I times sine theta. This is Euler's formula. To understand why this works, we need Taylor series. These infinite sums can represent functions. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on forever. Similarly, sine and cosine have their own series. Notice the alternating signs. Now substitute I theta for x in the exponential series. Watch what happens to the powers of I. The real parts become the cosine series. The imaginary parts become the sine series. They separate perfectly. Let's visualize this on the complex plane, where real numbers run horizontally and imaginary numbers run vertically. E to the I theta traces a point on the unit circle. The angle theta determines the position. As theta increases from 0 to 2 pi, the point traces a complete circle. Exponentials become rotations. Now what happens when theta equals pi? E to the I pi equals cosine pi plus I sine pi. Cosine pi is -1, sine pi is 0. Therefore, e to the I pi equals -1. Add 1 to both sides and we arrive at the most beautiful equation in mathematics. E to the I pi plus 1 equals 0. 5 fundamental constants united in one elegant equation. 0 and 1 from arithmetic, pi from geometry, e from analysis, I from algebra, all connected. Addition, multiplication, and exponentiation. the three fundamental operations of mathematics. This is why mathematicians call it the most beautiful equation ever discovered. Simple in form, profound in meaning. We've traveled through 2,500 years of mathematical discovery, from Pythagoras to Euler, from straight lines to circles, from certainty to probability. Each topic seems separate at first, yet they all share a profound connection. The Pythagorean theorem describes right triangles. Pi defines circles. Buffon's needle uses randomness. Euler's formula unites exponentials and trigonometry. But underneath, they all speak the same language, the language of geometry. Geometry isn't just about shapes on paper. It's the hidden structure of reality itself. The planets move in ellipses. Light travels in straight lines. Waves follow sinusoidal curves. Nature speaks in geometry. This is why geometry rules reality. Not because we invented it, but because we discovered it. Mathematics is not a collection of formulas to memorize. It's a lens through which we see the universe's deepest truths. The beauty we've explored today is just the beginning. There's an entire universe of mathematics waiting to be discovered. The geometry that rules reality. Simple in its principles, infinite in its applications, beautiful in its unity. Thank you for joining this journey through the mathematics that shapes our world.